Hello, 1102. Let's finish up our discussion with descriptive statistics. So we were talking about last time the difference between descriptive and inferential statistics. Descriptive statistics, we are describing a set of data using some values, some numbers to describe what the set of data is like. And we talked about that there are 4 moments of the data that give us some information about the data set. And the first moment was central tendency, which is the middlemost point of our distribution. And we can calculate this using a variety of different ways, 3 ways in which you've learned from, I don't know, elementary school, are the mean, the median, and the mode. We talked about how to calculate those and some of the characteristics of the mean, median, and the mode when we use each of these measures of central tendency depends on the scale of measurement of our dependent measure. So the second moment of data is variability. Now, the majority of questions that we ask in psychology have to do with mean differences. Is the mean of this group higher than the mean of this group? But a lot of questions that we're interested in deal with the spread of our data points. Are they all clumped together? Are they very spread out? So some of our research questions have to do about variability. And variability gives us some indication of, and we can use variability to look at mean differences. For instance, if our scores vary a lot and mean differences between 2 different conditions and experimental control conditions are very small, well then the differences between the 2 might be due to that natural variability. However, if our scores are not varying that much from one another, and yet there is a somewhat sizable difference between our experimental or control condition, it's very unlikely that those two means differ due to the natural variation that there typically is in these scores. So we can use variability to help conduct statistical tests. We can look at variability as an indication of how much error there is in our measurement. So variability is going to be very important for us, and moving forward in the psychology major, it's something that you need to be quite interested in when you're looking at your data set. So with variability, what we're looking at is how spread out our scores are. Are they grouped together or are they spread out? There are 3 different ways that we can look at variability. So first, let's look at 2 sets of data. So we've got 0, 10, 20, and a 9, 10, 11. Now the mean of both of these is 10. But the mean would not let you know how drastically different these data sets are. In the first data set, there's a lot of variability. In the second data set, there's not nearly as much variability. So we need some indication that lets us know something about variability. So the first way we can look at variability is with the range. Range is fairly easy to calculate. We take the highest value in the data set and we subtract it from the smallest value in our data set. So the range of this data set would be 11 minus 9, which would give us 2. And the value in the range in this data set would be 20, 20 minus 0. So the range is fine and good, but let's take for consideration the following 2 data sets. First data set 1, a bunch of 5s and a 9, and here we have 1, 2, 4, 5, 6, 8, 9. Now the range in both of these situations is 9 minus 1, which would be 8, but the variability is different. There's much more variability here in the second data set than this first data set. That's because the range only takes into account 2 values, the highest and the lowest. So the range isn't that good of a measure of variability. It looks at the 2 extremes, but it doesn't tell us the amount of variability if we're looking at the entire data set. So how should we go about looking at variability in the entire data set? Well, one way that we can do it is looking at something known as the variance. Okay, the variance is the average squared deviation of each number from the mean. So here's our formula right here. When we're looking at sample variance, we're using Latin letters, remember. We're using S squared. This is our symbol for the variance. And what we're doing is we're taking every individual score in our data set and subtracting it from the mean. And so when we do that, we take all of those scores and we square them, and then we add up all of those squared deviations from the mean, and then we divide it all by n minus 1. For this class, the denominator is always going to be n minus 1 because we're always dealing with sample means. Now, you might have learned if you have taken quantitative methods, or maybe if you've taken elementary statistics, that sometimes this denominator is just n. That's a biased formula for the variance and should only be used if we're talking about population variance. So here's the formula that I want you to use when we're looking at variance. Okay, so the top part of this equation has a special name. It goes by the sum of squared deviations, and sometimes called the sum of squares. Why? Because we are adding up squared deviations. Okay. Another point to note about the variance is that we are taking every score minus the mean. Well, why square it? What were to happen if we were to just take the deviation scores from the mean and add them all up? Well, some of them would be positive and some of them would be negative. And what happens if we do this with the mean is that those scores will always cancel out, the positive values and the negative values. And so we would always get a sum of average deviations would always be 0 for the mean. That's a special property of the mean. So we square everything to make things positive. But what this is also going to do is for values that are outliers, that are extremely far away from the mean, that this is going to lead them to heavily contribute to how much variation there is. Outliers are really going to up what our variance is. Another thing is that since we're squaring everything, the variance is always going to be positive, because when you square something, it's always going to be a positive value. Okay, and when we sum up all of those average deviation units, then we divide it by n minus 1. So if we have the following scores 1, 2, 4, 5, 6, 8, 9, what do we need to do with these? Well, the first thing that we need to do is find the mean. So we add them all up, divide by 7. This gives us a mean of 5. Then we're going to take all of these scores, subtract 5 from them. But again, remember, if we were to add all of these up, and you could do this yourself if you don't believe me, they would all add up to 0. And it doesn't matter, this isn't a special property of this data set, any data set, the sum of deviations would be 0. So we square them to make them all positive. We add all of these up, and then we divide them by n minus 1. So we're going to add 16 plus 9 plus 1 plus 0 plus 1 plus 9 plus 16. Then we're going to divide them by n minus 1. And since there's 7 scores, this would be 6. This is going to give us a variance of 8.67. So that's how we calculate the variance. And it's important that you know this formula and that you're able to calculate it yourself. One limitation of the variance, however, is that the variance is always in squared units. So if we're looking at a dependent measure of feet, our variance is always going to be in squared feet. If we're looking at the number of items someone remembers, it's always going to be, variance is always going to be in squared number of items that you can remember. So this is a bit awkward. So one thing that we might want to do is to convert the variance from squared units to the units of the dependent measure. And the way that we do this is by taking the square root of the variance, and this gives us a special measure of variability known as the standard deviation. What the standard deviation is it's just the square root of the variance. Because the variance is always positive, the standard deviation is always going to be positive as well. This is going to make the standard deviation probably the most popular measure of variability out there. Our symbol for standard deviation is either going to be a lowercase s or SD for standard deviation. Here we find our standard deviation is 2.94. Now, what's important to note is that if I give you the variance, you can convert it to the standard deviation. But if I give you the standard deviation, you can convert it to the variance as well. We just take the standard deviation and we square it, and multiply it by itself, and we're going to get the variance of the score. Sometimes with statistics, we need the variance for a formula. Sometimes we need the standard deviation for a formula. Well, it's easy to convert the two of them. As long as I give you one, you should be able to convert it to the other one of them. Okay, so that is variability, standard deviation, variance. How about the other moments of the data, the third and the fourth? Now, the reason that we call variance the second moment of our data is because in the formula for variance, we have a 2. Okay, we are squaring something with our data set. With measures of central tendency, when we're looking at something like the mean, we are squaring it by something, but by 1. Okay, anything raised to the 1th power is itself. So we can think of that kind of as the first moment of the data. Here's the second moment of the data. So the third moment of the data, skew, we're going to raise something by the 3rd power. Now, this formula is ugly. Do not memorize this. This is not important for you, but I do want you to note that there's a 3 here because it's the third moment of our data. So the skew tells us something about our distribution, whether or not we have outliers to the right of the data set or outliers to the left of the data set. Or maybe it's the case that we have an equal number of outliers. So it's whether or not our data set, if we look at it, is skewed to the left or skewed to the right. The majority of values are either on the lower end of the data set or the upper end of the data set. We can look at this we can examine this by looking at the tail of our distribution, and this is going to tell us whether or not we have skew in our data set. If skew is close to 0, this means our data set is going to be symmetric about the mean. If our data set is skewed, it's not going to be symmetric. So let's take a look at some distributions that have skew. So here, what we're looking at, something that we're going to look at a lot next lecture, is a probability density function. What this is showing us is on the y-axis we have frequency. Well, actually we have probability. Okay, how likely we are to find a score of this particular value. And on the x-axis we have the specific scores. So what's the probability of us obtaining a score around right here? Well, we'd have to go up to where the line is, and we see on the y-axis, what is that probability? So we know the frequency of obtaining particular scores with our probability density functions, more about which when we talk about normal distributions. So the majority of our values for this graph are here over to the left. Majority of values that we have for this graph are over to our right. Notice that the mode, the most frequent score, is at the top of these peaks. Our means are probably somewhere around here for this graph and probably over here for this other graph. Notice that the distributions are not symmetric about this point. If we were to draw a line straight down of the mean and fold the graph in on itself, they wouldn't match up perfectly and be mirror reversed images of one another. This first graph is positively skewed. This data set is positively skewed because the tail, we have a few scores that score extremely high compared to the mean. For our graph to the right here, we have negative skew. We've got some values that are much lower than what the mean is. We have some outliers to the left of the distribution. Okay, the tail is going to tell you whether or not we have a negative skew or positive skew. If the tail is to the right, we have positive skew, and if we have a tail to the left, we have negative skew. Skew is important. It lets us know if we have any outliers or where those outliers particularly are. And one of the assumptions for a lot of the statistics that we use in psychology is that we have a normally distributed data set. And if we have a problem with skew, if we have data that's heavily skewed, we don't have a normal distribution. So we might have to use a different statistic. So that's one of the reasons why skew is important. That's the third moment of our data. Let's talk about the fourth moment of our data. And this is kurtosis. Fourth moment, we're raising something to the fourth power. Again, do not memorize this formula. That is not important. But kurtosis is the degree to which our distribution is very peaked, or is it very flat? Is it overly peaked, or is it overly flat? We'll see some examples of this here shortly. Okay, kurtosis for a normal distribution will be 0. It will be not super peaked, it will not be super flat, and will have a characteristic curve. Positive values are going to lead our data set to be more heavily peaked. More values will be in the middle, and lower values, values less than 0, are going to indicate that our data set is more flat. There's special terms that we use to describe data sets that are very peaked and that are very flat. So first of all, notice that this black line right here is our normal distribution. It has an average amount of flatness and peakedness. When our kurtosis is higher than 0, we get a distribution that is more heavily peaked, and we call this distribution leptokurtic. Leptokurtic. When we have a distribution that's overly flat, we call the distribution platykurtic. This distribution is going to be more flat or flatter than a normal distribution. Okay, how do you remember this? Well, the way that I always remember this is that platy, plat is like, it comes from the Greek for like broad or flat. And Plato is not actually Plato the philosopher's actual name. It is a nickname because when he would wrestle back in ancient Greece, he had very broad, wide shoulders, and so that was his nickname. So that's how I remember that platy means flat. And of course, I told my wife this, and she's like, wow, why would you tell your students that? How are they ever going to remember that? For her, platy means flatty. So platy, flatty, and then lepto is more peaked. So however you remember it, Plato or platy equals flatty, doesn't matter, just make sure that you know the difference here. If this were class, I'd do a little ballet demonstration with the leptokurtic, and then the, I don't know what ballet move this is, plie, I don't know, with the platykurtic distributions. Okay, so these are ways in which we can describe our data set. Next lecture, we're going to talk about the wonderful world of normal distributions and what normal distributions can tell us. All right, have a wonderful day, and I will talk with you later. Bye-bye.